The only thing I'm adding today to these inclined plane questions is one force. I'm adding one force to these questions. It's friction. Okay? And we know that friction always opposes the motion. So if you know that the block is going to slide down the ramp, then friction has to act in the opposite direction. And that's it. You're just going to have one more force acting in your x direction. Okay? And so really a lot of this comes down to, can you guys draw free body diagrams? Okay, these are going to be your best friend for these kind of questions, right? So right off the top, you're holding a 85 kilogram trunk, and I think we kind of saw a question like this already. It didn't have friction in it. At the top of a ramp that slopes from a moving van to the ground, making an angle of 35 degrees with the ground. You lose your grip and the trunk begins to slide. Okay, we want to find the coefficient of friction. Oh, it told us that. Sorry, no. We want to find the acceleration. Sorry. You wouldn't know I did these questions already this morning. I did too many of them. Okay. And then we want to find, okay, well, if the trunk slides for 1.3 meters, how long did the motion actually take? Those are the two questions that we're going to answer here. Okay. So let's start with the free body diagram. Okay, I'm going to draw my ramp. And I know the ramp makes a 35 degree angle with the ground. And I'm going to draw my box. Right? We know, and right off the top, I'm going to set up my coordinate system to be tilted like this, right? We saw some of this already too, where down the ramp is acting in the positive x direction. Up would be positive y, down negative y, and backwards is negative x. Okay, and so we have the normal force from the contact with the ramp. And we recall when we were drawing questions like this that the force of gravity you can't just change the angle which gravity acts. It still always has to act straight down. So straight down looks like this. FG. Okay, I drew that a little bit bigger because these should be relatively close in size. Okay, I'm just drawing that big because we need to be able to see the components in here. Okay. Now, this is obviously acting at an angle relative to our coordinate system, right? Like it's acting straight down. I don't mean to draw that blue, but it's acting straight down. So it's at an angle relative to the coordinate system that we've drawn. So angles mean components, right? How do I break that into components? Well, let me get rid of that and this. Well, straight down and horizontally. How do we figure out what those are? Well, we know the force of gravity is equal to mg. Okay, so if I'm breaking down the force of gravity, then I should expect to see the blue piece is adjacent to the angle, and so we get cosine. So mg cos theta. And the red piece is opposite mg sine theta. Okay? And we have one more force now. That's what we've seen so far, right? And we have one more force. We know that this thing's sliding down the ramp. And if it's going down the ramp, then we must know that friction is acting in the opposite direction. So we have this force of friction in the negative direction. Okay. Now, just before we get too carried away, we know, or we learned in our friction lesson from yesterday, that the force of friction is equal to, well, we saw that the force of friction was two parts. One was the weight, right? And one was how rough the surface was. That's how we figure out how friction is going to act, or at least qualitatively, right? So describing how much friction we could probably see. Not numerically, but just, is it going to be a lot? Is it going to be a little, right? Those were the two factors, weight and how rough the surface was, right? Weight of the object. So that's what this is. Fn, sorry, Fn, you guys know Fn has to equal, let's take a look here. I'm going to zoom in. Fn has to be equal and opposite to this blue component, right? They're opposites. So Fn must be equal to mg cos theta. Those are the only two forces acting in the y direction. So when I look at these questions, we know if I were to do, oh my goodness, look at that sigma. If I were to look at the sum of the forces in the y direction, we know that this block is not going to just jump off the ramp, right? We know that it's 0. So this equation is not, like the forces acting in the y direction are not interesting from the standpoint that nothing interesting is happening. They're just balanced, right? So there's not a lot of information to be found from looking at the y components here, or the forces acting in the y direction, right? The only thing it's good for is identifying that the force of friction is actually equal to mu mg cos theta, right? That's all it's used for. So if I actually run through that, what are you going to see? Well, you're going to see a positive Fn, and we're going to see the negative force of friction. And that has to equal 0, right? Those are the only two, not force of friction, silly me. Fg, sorry. Right? But it has to be that piece, or sorry, the y piece, right? So what's it actually equal to? Well, it's mg cos theta. And those two forces have to equal 0. Those are the only two things acting in the y direction. So what is the y used for? Well, y is used for solving for the actual value of Fn. And that's it, right? Something we already kind of know, right? Well, if I'm just going to rearrange this equation, Fn has to equal mg cos theta. We know that. That's all the y is really used for. So it's not that interesting for the, like, you guys know, unless there's a third force, like, I don't know, tension being applied in the y direction that affects the normal force, not that interesting, right? You just guys, the only time you got to pay attention to the y direction is if you know that the normal force is not going to be equal and opposite to this blue component, right? So the interesting part of these questions is that the block is accelerating along the x-axis, right? So that is what's interesting. But the problem is we have this force of friction buried in there, right? Which we need the normal force for, right? In order to figure out what the force of friction actually is, okay? And so we have to find it using the y. That's what it's there for, okay? So if I actually go to find the acceleration of this box, I'm looking at the two forces that are acting in the x direction. Well, what are the two forces that I have? Well, let's look. So the sum of the forces in the x direction has to equal ma, right? Which two forces, or what's the sum of the forces in the x direction? Well, I really only think I have the one, right? Oh no, two. Sorry. I have this one. Mg sine theta is acting in the positive x direction, right? So we have positive mg sine theta, and force of friction is acting in the negative direction. So the force of friction is equal to ma. Okay, and we know what the force of friction is now. I won't erase that, right? The force of friction is right here for the reasonings of the sum of the forces in the y direction are equal to 0, okay? So what do you do with that? Well, you just take this. That is the force of friction. You plug it in there. So what do you get? You get positive mg sine theta minus mu mg cos theta. And that has to equal the mass times the acceleration. Anybody have any problems with that so far? you should find at this point in time, you'll have all the information that you need. Now, what's cool about this question? Oh, you know what? As I'm thinking about this, I forgot to look into the Hot Wheels question. I'll look at that. Okay, that's intriguing. I have to think about that one again. I forgot. And the reason why that made me think of that was because yesterday we saw that the mass of the box in this particular question isn't really actually that relevant, for the reason that I only have one mass. It's right here. So if there was ever an instance, and I'm showing you this because sometimes you might come across a question that the question doesn't give you the mass of the box. And you'd be like, I don't know how to do this question because it hasn't given me enough information to do it. Well, it has. You guys know, here's term 1. This is a math. I'm speaking math now. Okay, forget about the physics. Physics is actually pretty much over now. The physics ended probably about here, where you set up the question. Now it's all math where we're going to actually solve, right? So this is the physics up here, and now we're in the math. Okay, so change your lens for a second and just look at this. Okay, there's a whole bunch of variables there. You know some of them numerically. But let's just think here. I have a term 1 and I have term 2, right? In term 1, it looks like I have a mass, and in term 2, I have a mass. So if I have something of the same, like if I have the same thing appearing in 2 different terms, we can factor. What kind of factor? We would call that the greatest common factor, and in this instance, the greatest common factor is going to be the m. So I can remove that m value from those 2 pieces, term 1, term 2, and what do you get? You get this. G sine theta minus mu g cos theta. Now, what happens if I divide both sides by mass? So the acceleration is equal to this. Now, that looks scary, and I know I scared some of you. I know I've scared some of you in looking at that and going, why hasn't he plugged in the numbers? I didn't plug in the numbers for a couple different reasons, right? And I think we've discussed some of these reasons. One is the longer you can delay plugging in numbers, you get less rounding error. Right? And also less opportunity to make a calculator error, right? We'll call it less human calculator error. All right, so you guys not like plugging in a number or like, I don't know, forgetting a negative or something. Okay, I think am I okay with you guys plugging in letters here? Or numbers for where you know the values? Absolutely. Okay, don't think I'm not going to give you marks for plugging in numbers where you see numbers. And if that's what you guys are comfortable with for the first time seeing physics, do that. Okay, all I'm saying is you guys will see variances in what you guys get in your test answers and what I get in my solution, right? Sometimes that's because I do questions like this and you guys do questions like typing in numbers all the time. Where it's going to come into to be a real pain, and the reason why I'm talking about this, and where this stuff starts to come in more, is when we get into things where you're typing in scientific notation. Or like 9.053 times 10 to the negative. If you forgot the -3, your answer is going to be just ridiculous, right? And so I show you this stuff because you don't want to have to type in these numbers over and over and over and over and over again, every line, right? And deal with things like that. Okay? So, when you can, do questions algebraically, right? Just have the algebra skills. All we've done there is factored and canceled, right? Now, it's at this stage we know what acceleration is equal to in terms of the algebra. Now we can go in and plug in our numbers, right? So A should be equal to, and I wrote down this answer here, so I'm just going to scoot through it, okay? I'm going to plug in the numbers, but so you guys can see what's going on. Actually, I don't even think I need that. Sine 35. The other thing about having the algebra, now that I'm writing this, if you guys are if you have a question that looks like this basically the exact same question, which you will have, right? This algebraic expression, it's like, this is almost like a kinematic equation now. Like something you could put on your formula sheet and say, this is the acceleration of a block accelerating down an incline, right? It's like the algebra has been done for you. All of this work, all of it, has arrived to here. That's what this is good for. This would be like an equation on an equation sheet, where you would use this specifically for a question where the block is accelerating down an incline, right? You know what it is algebraically now. That's what's kind of cool as you guys go forward in physics or science in general, right? This is what we call, a fancy name for this is a derivation. So where we get equations from, dimensional analysis, things like that, is a derivation. I would prefer, Elizabeth, if you guys could just do all the work, so that I know you know how to do it. What I'm bringing to your attention, and I might choose to do something tricky, Elizabeth. Not tricky, but like you guys will be able to do this. But I would prefer you guys be able to do all this work, okay? So that I know that you know how to do it. Okay, but this word will come up. Okay, it's a derivation. And it shows you where equations come from. Okay, but I could very easily make a little tweak in there and really throw a wrench. Like maybe I push the block up the incline with an applied force, and friction's acting, and you know what I mean, Elizabeth? You'd have to be able to do all this work. This is just for if something's going down an incline. Okay. So anyway, I'm doing a lot of talking aside from outside of the question. My point is, don't be scared by this stuff. It's doable, right? Right? And when you type this into your calculator, you just get a nice number. The other thing, Elizabeth, I suppose you could use this for, I don't need a, well, yeah, I guess. Sorry, Elizabeth. The other thing you could use this for is you guys go on a test, you do all the work. I don't have an answer there to tell you if you're right or wrong. You guys go back in your notes and you say, oh, I wonder if my answer is right. Well, we can check it. Okay? As long as all the parameters fit that question, then that should work. If I ask you for the other thing, Elizabeth, is what do you do if I ask you for, I don't know, the coefficient of friction instead of the acceleration, or something else? What if I ask you for something else, like the mass, right? Because I could do anything. Right? You guys have to be able to do all this work. In the event I ask you for a different piece of information instead of the acceleration. Okay. Now I've only answered one part of the question here. I don't think we're gonna finish both these questions, or all three of these. So we'll do number 2, and that'll probably be at 11 o'clock. So that's part A. We found the acceleration, right? And something to notice, the acceleration I said as a vector, I had the magnitude of 2.25 meters per second squared, but I drew the vector because it's going down the ramp. I specified that it's going down the ramp, not up the ramp, right? Okay, they didn't whoever made this question didn't put that down the ramp, but just something to be aware of, okay? That would be the direction for this question if you guys wanted to say that, okay? Not gonna be too picky on something like that. Don't stress like, oh, I gotta put I didn't put the direct. For some questions like impact velocity on the test, I need the direction, right? Something like that. Okay, sorry, I'm getting all derailed here. Let's do the second part of this question, which is not too bad. We want to find the time that it took for this thing to slide down the incline. Okay, let me do some shrinking here. Save us some space. Okay. So, where's my solution here? Let's take a look at the stuff that we have, what we know. We know delta D is equal to 1.3 meters. It's not even really delta D, it's how far down the ramp it went. So we know that it slid 1.3 meters, right? It's not really a displacement. T equals question mark. A we now know is 2.25. And VI equals 0, right? We released it from rest. And so we could find, using this information, we can use I don't need delta D. D equals VIT plus half AT squared. You just plug in the stuff you know. You know VI is 0, right? So that's going to go away. You know D is 1.3. That's going to be equal to 1/2 AT squared. I'll plug in the acceleration. Okay, and then you know T is equal to, if you do the math on all that, 1.07 seconds. Okay, that's a lot. Like, obviously, we're not going to do that much talking. It's not going to take you 20 minutes to do these questions, right? I'm just stepping you through all this. Okay. What's it start with? The free body diagram, right? I would start with the X because that's the interesting motion, right? What's the only problem with starting with the X? You don't know Fn, but you do know Fn for a ramp, right? You know the normal force has to be equal and opposite to mg cos theta, right? The blue vector. So then you know the frictional force, and you just do this question accordingly. Okay, I did a lot of extra talking in there, obviously. Okay. These are just things that are coming to my head as I run through this question. You can see where the physics ends. This is all math. These are math skills that you all have. I'd imagine at this point in Octo 8 of your third year of high school, the math won't be the struggle. Hopefully. There might be a couple little hiccup things. That's fine. We can deal with those. But you have all taken the 3U math, which is I hope, not that I hope, but you should have by this point, I think, where your math skills aren't that, like, they're pretty strong, right? And so this shouldn't be the issue. This is the issue, setting it up. That's where kids have problems, okay? Does anybody have any questions? Okay, the second one's kind of a bear of a question. This is a little bit harder. It's harder because there's just more information. That's it. You're going to attack this problem the exact same way. Okay? The exact same way you're going to attack this problem. So first things first, I need a free body diagram to represent this situation. Now, the one thing I got taught, well, I got taught lots of things in grade 12 physics, but this looks kind of, I don't like the look of that. And you're going to try and squeeze things onto the diagram. You're going to, like, it's just going to look messy. Okay, so what we do when we draw the free body diagram for this is what my physics teacher taught me. We take it and we draw the system horizontally. Okay, so what does that mean? Well, it means I have a block here. It'll be the 2 kilogram block. And I connect it with a string over to here, to the 7 kilogram block. What are you going to do now? Well, you just draw the forces on it, right? Well, it looks like we've got some tension, right? And we've got tension here. It's the same tension force because it's the same piece of string, right? It's a continuous piece of string. Okay, that's a 7, not a 2. Okay, and we're just going to draw all the forces that are acting on here. Okay, we know as soon as you let go of the system, the block should accelerate in this direction, as long as like the frictional forces aren't too much that it's static. Okay, as long as the static friction isn't greater than the downward force of that block, the system's going to move. So it's going to do this, right? Something like this. Okay, and I told you the value of that acceleration. That's going to come into play after. I realized that after I did the whole question. Okay, so we just got to draw all our forces in the normal fashion, but just keep in mind, like if I was to just sketch it here, the force of gravity acts straight down. So when you tilt this, the force of gravity is kind of like this. And on this one, it's over in this direction. That's the only little trick with this. But it makes, the reason why I'm doing this is it makes the coordinate system a little bit easier. Okay, everything acting in this direction is positive, and this is negative. Okay. And you just draw all your forces on. Well, the force of gravity, we can break that into its component. Right? This will be mg cos theta, mg cos theta, and then we have mg sine theta, right? And then on these as well, I've got the normal forces and the normal force. Okay? I don't think I've missed anything. That's it. Oh, sorry. So, yeah, I missed the big one. So if this system, and this is why I mentioned this at the beginning, if it's moving this way, that means that friction must act this way. And friction must act this way. So you're going to have a friction force this way and a force of friction force this way. Okay, that's your free body diagram, right? And I think it sums everything up pretty nicely. You can see exactly where all those forces are acting, what directions, right? Okay. Anybody have any questions, comments, concerns about that one? The way I've set that up? When I see problems like this, I just, I don't know. I don't know if it's the same for everybody, but I just found comfort in seeing this thing horizontally instead of having this thing. Where do we draw the angle for the incline? Sorry, Elizabeth. It's still in here. Okay, there's like what I've done is I've tried to take this question and just get rid of the fact that it's on an incline, but still applying like the rules that it's still an incline. It's just for solving purposes and visualization, right? It's the angle's still there. Like the angle for between FG and its vertical component can't change, right? Has to be 35. Okay. So now we just go ahead with our solving, except this time is a little bit more complicated. That's all. I think the physics is almost done. We just have to set up, we're just going to set up our forces and how they're acting, right? The thing with this question is we have two masses now on inclines, which is kind of tricky, right? So, for this question, we're going to say, okay, well, I have block A. What's going on in block A? Well, like I said in the first question, there's nothing too interesting going on in the y direction here, right? Especially when we're thinking about, like, the blocks are not jumping off the ramp. There's nothing too interesting going on, right? And so what am I interested in? Well, I'm kind of interested in just the motion in the x direction, right? Left and right. Why do I care about the y direction? Well, it allows me to solve for the normal force, which dictates how much friction I'm experiencing, right? So there's, I don't know why I wrote y after saying the important part is x, okay? So we're going to have some of the forces in the x direction on this question, right? Well, let's look at block 2, or block A. We'll call this block A and block B. Okay. Let's look at the forces. Well, what force is going on in the x direction? Well, we got the negative force of friction, and we got positive tension, right? That takes care of, there's the force, negative force of friction, positive tension, and the only other force I see acting in the x direction here is this one, minus mg sine theta. Okay? We know force of friction is negative mu Fn plus tension, that's equal to ma, sorry, minus mg sine theta. Okay? We'll do one more line here, and then we'll plug in some numbers, because I think the numbers make this question a little bit easier. Manageable for everybody. We get negative mu mg cosine, right? What does Fn equal to? Just to recap, Fn is equal to mg cos theta. Fn mg cos theta plus tension minus mg sine theta. Okay. We are now in a position, I'll say, for these kind of questions, if I ever give you one of these, okay, plug in the numbers that you know. The only thing is I don't know, I'm trying to solve for the coefficient of kinetic friction, okay, so I don't know that. But you do know everything else. You know the fact that the mass is 2, you know the theta, you know g, you don't know tension, that's a problem, and that's part B. And you know all the masses and the thetas, right? So that's, we're just going to plug in those numbers, okay? So I don't know mu, so it's negative mu, but I do know that it's 2 times 9.8 times the cosine of 35 plus tension minus 2 times 9.8 times sine 35 is equal to 2 times 1.5. Where's the 1.5 from? The acceleration of the system. Okay? Now you can just type all that into your calculator and clean it up, and it turns into something quite nice, actually. Okay? Something that should look very, very familiar to you. Okay? So let's just take a look. I'm going to get, I already did this, so I won't slow this process down. Cos 35, this should be negative 16 mu. Right? Like this number, all this here. All this should turn into negative 16. And then we have plus tension. And then the sine piece, that should be minus 11.24. Right? That's all this. And then that's going to be equal to 3. Okay, so let's just clean this up. Okay, this is, what stage are we at? We're going to collect like terms. Okay, that's all we're doing. So and in the midst of it, I'm going to do something strategic here. I'm going to move this to the other side. I'm going to take this and bring it over here. Okay, so I'm going to get negative t is equal to all right. Is anybody freaking out right now? Please say yes or no. All I've done is I've looked at the forces acting on the box in the x direction for the 2 kilogram box. Okay. This looks okay. Like, this is nothing different than, you guys have seen something that looks like this before. Y equals negative 16x minus 14.24. That's what this is. This is a line. Grade 9 math. Okay, it's a line. That's all that is. Okay? You have two variables there that you don't know. That's not a problem. We've dealt with lots of questions where we have two variables and we don't know what they are. Okay? The problem is that I don't have two equations currently. Okay? But the nice thing is I have two boxes in this question. Right? And so you guys can go. Well, let's just, for 2 seconds here, let's take a look at, I'm going to move this up, save myself some space. Let's, for 2 seconds, just let's look at the sum of the forces acting on box B and figure out what's going on there. I'm going to save some space here. Okay. Well, let's look at box B then. Okay. We're going to do the same thing. What do I got acting on box B? Well, looks like I've got negative tension and negative force of friction and positive this time, positive mg sine theta equals ma. Okay. So what do we do? Well, let's just start figuring out, well, it's the same thing, right? You know the force of friction is going to turn into and now we're at this stage, let's just plug in some numbers, right? I don't know tension, that's fine. Then I've got, oh, I don't know mu, that's also fine. But then I know everything else. I know the mass of block B is 7 times 9.8 times cosine of 35 plus 7 times 9.8 sine 35 is equal to 7 times 1.5. There's only two things you don't know. Oh, conveniently, it's the same two things I don't know over here. You can see where we're going, hopefully. Well, let's just clean this up. We're just going to get some numbers and clean it up, right? You should see, if I were to clean all this up, should see negative t, and then on the mu value, I should see negative 56.2 mu. Okay. And then positive okay, you can see where all this came from. This goes to there, the 56.2. This all here will be the 39.3, and this is the 10.5. And you just clean it up the exact same way we did before, okay? But I'm going to strategically do something. I'm going to bring this to the other side, and I'm going to take this and put it to the other side. All right, and what you're going to get is positive t is equal to negative 56.2 mu plus 39.3 minus 10.5. And if I clean that up, I'm going to get an equation that looks like that's it. Now, I know at this point, I've done a lot of talking. I know. Okay. Does anybody get the point of this? Does anybody know what I'm going to do next? Just out of sheer curiosity. I promise this question's almost over. About 2 minutes left to work here. Okay, Elizabeth says, we can substitute. Now the problem, yes, Elizabeth, you can substitute. Why is Elizabeth saying substitution? Well, she's saying substitution because we have two equations and two unknowns, right? Now, Elizabeth, I've done something strategic, and I've done this because I've done this a few times, and I know that this works better. And you guys will remember, at least I teach this in the grade 10 academic course when I teach this. There are certain instances where substitution is a better method than its counterpart, elimination, and vice versa. Well, it turns out, well, you guys have done all the hard work in the physics, right? This is all like physics. Now you're just going to do a little bit of math. But it looks like if I were to do elimination here, all I would have to do is take this equation that I've written here, number 2. I'm going to try and just highlight the equation, not even the box. Okay, I'm going to take it and I'm just going to move it from here over to here. And what happens? Well, it looks like I can add these two equations together. And what happens? Well, look, we're here. Negative t plus t, that's 0t. And that's now equal to, well, I don't know, what does this equal? Negative 16 plus negative 56.2. What's that? Well, without getting too complicated, I think it should be around negative 72.2 mu. And then you do this. You should get 14.6 for that. What do you do next? Well, you just solve for mu. What is the coefficient? That's what we're after, okay? We did all this work. And this why, Elizabeth, having the skills that I've taught you in question A, I know we asked, oh, what's about the acceleration, but you can see how it's something as simple as asking for the coefficient of kinetic friction, and I provide you with the acceleration. It kind of changes the way that like this question is going to pan out. I know I added a second block, but you know, we set this question up the exact same way, and all we did was do twice the amount of work, right? We've basically done 2 questions here to be able to solve for 2 different kinds of pieces of information. That's it, right? So I've eliminated tension. So I just bring this over and I get negative 72.2 mu is equal to 14.6. Well, you guys know how to solve that. You divide both sides by, when I move it over, it becomes positive. Right? Just divide both sides by 72.2, and what do you get? You should get a mu value of 0.2. That's how much how rough, that's describing how rough the surface is. Not very rough at all, right? For this question. Okay. Now we have one thing left to do. I now know what mu is. Well, you have 2 equations that describe how to find tension. That's part B. So just use it. T equals you take mu and you plug it in for where you see it in that equation. You get tension should be equal to you should get that was a lot, guys. Okay, but we have to, if you guys haven't done any questions, like homework questions around like free body diagrams or like the friction forces, frictionless inclined plane questions, right? That was a great. You got like 3 examples there of how to set up a sum of forces statement, right? So I know that took a bunch of time, but if you guys sat and watched that, I did 3 questions there where all I did was add up the forces that were acting in the x direction, right? It's the same thing 3 times. The only thing that changes is what kind of forces are there. In this question, I introduced tension. That's what I was getting at in the first part, Elizabeth, was if I introduce a force like tension, now the problem changes because you don't just have friction and the acceleration due to gravity down the ramp. Right? We've thrown a wrench in there. And so being able to write a free body diagram and work through the problem accordingly, just by adding up the forces that are acting in x and y independently, That's all I can do. So if I teach you that process, you can do any question. It doesn't matter what it is. You guys can do it. Okay. So wrapping up that question, that's a big question, right? Grade 11s, the chances of me asking you that particular question on a summative pretty low, right? That's a very loaded, that's a grade 12 question, I would say. Okay. But you can see that is all the content that I've taught you over the last few days, just into some bigger question. The reason why I show you that is grade 11s are required for this afternoon's lesson. You guys have to be able to solve questions using substitution and elimination. Okay, so this is a precursor to this afternoon's lesson. And what's nice about this afternoon's lesson is this question 3, like it's related to the kinds of questions that we're going to do this afternoon. Okay, so we'll pick up with number 3 this afternoon at 1 o'clock, and then the other 2 questions are very close to that. Okay, I would arguably say easier than question 3. Okay. And when I say grade 12s, I mean the 4 U's, not the 4 C's. Okay, so the 4 C's and 3 U's, I probably won't give you a question like this on a summative. Okay, but I'll give you, let me clarify, I will give you a question on a summative that just has one block and you have to do all of this work. That I will give you. Okay, but you can see, and the nice thing about you guys taking the course with the 4 U's, for those of you in the 3U, you can see the extension on what it is we've done in grade 11 to grade 12. Okay, this is just one example. Okay. Does anybody have any questions before we go? Don't think that, before you guys go, don't think, oh, he said it was a grade 12 question. I'm never going to, like, you can see that that's not the case. Okay. You guys there's skills in there that you guys need. Okay. That is a half of that. If I cut that question in half, that's a fair question for you. Okay, so don't just think, oh, he said it was a grade 12 question. I don't need to know that. You need to know those skills. I've picked this question strategically so that I could show you 3 examples of how to add up forces. Okay, on top of what we've already done. Okay, that's why I picked that question. For the other reason, you guys have to be able to know how to solve for 2 oops, I don't want the eraser on. You have to be able to solve for 2 variables as well this afternoon. Okay, so there's some method to the madness here. Okay, is everybody okay? Don't be stressed. Okay. Okay, I'm gonna stop the recording there.